Okay, let's finish up section 5.2, day 1. We have another day after this, but to finish up day 1, this is the back page of the first page of notes, and we start with finding the exact values of trigonometric functions for some angle theta. Now, before we were given two sides of a triangle, we were given maybe the two legs or a leg and a hypotenuse, and that allowed us to find the other side, and then we just used the definition of the trigonometric functions to find the trigonometric functions of that angle theta, whatever it was. Here we're not told sides of a triangle directly, we're just told something about theta. We're told that cotangent theta is 7/24. We have to go back and think about what the definition of cotangent theta is. Tangent theta is opposite over adjacent, so cotangent theta is adjacent over opposite, and that means for this angle, 7 is the adjacent side and 24 is the opposite side. Now, I'm not told which angle theta is. I can see the right angle, and either one of my acute angles could be theta. That's up to me. But I do need to label it, because after I label theta, that determines which side is the adjacent side and which side is the opposite side. If I choose theta to be this acute angle, then the adjacent side is here, and it's 7. The side opposite theta is 24, and you should be getting good now at Pythagorean triples, using the Pythagorean theorem to find the hypotenuse. Hypotenuse is just leg squared plus leg squared, so that's 49 plus 576 is 625, and the square root of 625 is 25. 7, 24, 25 is a Pythagorean triple. And if you just want to check that, because I did it in my head pretty quickly, 24 squared plus 7 squared, I'm going to go ahead and say that's 49. Sure enough, that's 625, and the square root of 625 is 25. So there's the hypotenuse. Now I have the same thing that I did on previous problems. I can say sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And tangent theta is opposite over adjacent. And that kind of serves as a check, because we were given that cotangent theta is 7/24, so we should get for tangent theta 24 over 7. And then find each of the reciprocal functions. Cosecant theta is 25/24, secant theta is 25/7, and tangent theta is, or excuse me, cotangent theta, well, that's what we were given, 7/24. All right, let's do one more example like that. In number 22, we're given that cosecant of theta equals 4. If cosecant is hard for your brain to deal with, you can just change it to sine by saying if cosecant of theta is 4, then what is sine of theta? Well, if cosecant is 4, sine is 1 over 4, because cosecant is the reciprocal of sine. I know that, excuse me, the definition of sine is opposite over hypotenuse. So any, many, miny, mo, I can let either acute angle be theta, but once I've chosen theta, the opposite side has to be 1, and the hypotenuse has to be 4. And I find the other leg by using the Pythagorean theorem. When I have the hypotenuse and one leg, the other leg is the square root of hypotenuse squared minus leg squared, or 16 minus 1 is 15. So the adjacent side of that angle is square root of 15. Now we can say Sine theta, well, we already said if cosecant is 4, then sine theta is 1/4. But that agrees with the picture that we've drawn, opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse, square root of 15 over 4. And tangent theta is opposite over adjacent, 1 over square root of 15. And on the test, I will either tell you you don't have to rationalize it, or I will take either answer, rationalized or not rationalized. Now we can get these three reciprocal values. If sine of theta is 4, cosecant of theta, if sine of theta is 1/4, cosecant theta is 4, that's what we were given. If cosine theta is square root of 15 over 4, secant theta is 4 over square root of 15. And if tangent theta is 1 over square root of 15, then cotangent theta is just square root of 15 over 1, or just square root of 15. All right, so we have seen that if you are given two sides of a right triangle, you can find the third side, and then you can find all of the trigonometric functions of one of the acute angles. Or if we're given some information about one of the angles, that's really the same thing. It's giving us two sides of the triangle. We can find the third, and then we can find all 6 trigonometric functions. All right. Most of the trigonometric applications that we're going to do are pretty simple, straightforward. The hardest part is figuring out how to label a triangle. Number 24 says the peak of Mount Fuji is approximately 12,400 feet high. So I suppose this is the peak of Mount Fuji, and I'm going to label that 12,400 feet high. A trigonometry student several miles away, maybe this is where my trigonometry student is standing, notes that the angle between level ground and the peak is 30 degrees. So here's my level ground, and here's the angle between level ground and the peak. It wouldn't be up here because that doesn't include level ground. It would be here. Estimate the distance from the student to the point on level ground directly beneath the peak. So this is what we're looking for, one of the legs. And we don't know what the hypotenuse is. All we know is this leg, and this angle is 30 degrees. If A is the distance we're looking for, then we need a trigonometric function of 30 degrees that would involve the opposite side and the adjacent side. Which trig function involves opposite and adjacent? That would be tangent. So tangent 30 degrees is 12,400 over A. And we can solve that. We can look at the table of values if we don't have tangent of 30 degrees memorized yet. Remember, that was given to you on a page in a book that I told you that you didn't have to memorize. There's something I wanted to show you, though. I don't want you to worry about something that you're not supposed to know yet. Let me just do a side calculation here. 30 degrees. Let me just tell you, if I looked the value of 30 degrees up on that table, which very soon I won't have to do, I would get that tangent 30 degrees is square root of 3 over 3. And so that's what equals 12,400 over A. And I can solve that proportion by cross multiplying. Square root of 3 times A is 3 times 12,400. That would be 37,200, I think. Yep. And then divide both sides by square root of 3. A would be 37,200 divided by square root of 3. To the nearest whole foot, it looks like the distance between the student and the point on the ground directly beneath the peak is 21,477 feet. Now, I like to check my answers because, you know, every once in a while I do something goofy. What number is that? Number 24? Yes, that's what I got earlier, 21,477 feet. All right, let's talk about the calculator a little more. You're going to find, as you did with logarithms, that there are fabulous frontwards calculators and there are cursed backwards calculators, and I don't know which one you have. So I'm going to show you how I enter trigonometric values or trigonometric expressions on my calculator, and if you have a different calculator, you just may have to Google how to find tangent of 27 degrees on your calculator, something like that. In college algebra, the calculator that I call the fabulous frontwards calculator is the one that if you want to find the log of 1, you enter log or press log and then 1, and the calculator gives you the answer 0. The cursed backwards calculator is where you have to enter the 1 and then the log to get the same answer. So I have the cursed backwards calculator, which is okay. It's just whatever you get used to using. If I want the trigonometric function of some angle, I have to enter the angle first and then press the trig function. One other thing I need to tell you, in case you've never noticed it before, at the top of your calculator, pretty much regardless of what calculator you have, it either says in very tiny writing, rad or DEG or something else. That's the mode of the calculator, and I changed the mode of the calculator with this button. Right now it says RAD. If I press the degree button once, it's changed to grad. That's gradients, and we're not going to use those in this class. Press that button again, and now it says degrees. So if I want to enter any angle in degree form, then I need to have my calculator in degree mode. Now, I've already entered the next few problems on my calculator. You can grab your calculator and pause the video and check and make sure you're getting the same answer I am on each problem. Number 30, part A, is tangent of 280 degrees. I'm going to check that my calculator's in degree mode, and then, because I have the cursed backwards calculator, I'm going to have to enter the 282 before I press the tangent button. And I get negative 4.70, round to whatever the directions say. Here it said 4 decimal places, or I added 4 decimal places, so that would be negative 4.7046. If you have the cursed, well, no, if you have the fabulous frontwards calculator, then you enter it exactly the way it looks left to right, the tangent before the 282 degrees. The next problem is cotangent of negative 81 degrees. And I don't have a cotangent button on my calculator. I have a tangent button, but no cotangent button. So here's how I'm going to deal with that on my cursed backwards calculator. I'm going to first enter the 81 and make sure my calculator's in degree mode. It is, so I can enter the 81, and then because this is the cursed backwards calculator, and then make it negative. Now, like I said, I want cotangent of negative 81, but I don't have a cotangent button. I can take the tangent of negative 81, and then the reciprocal of that. Here's my reciprocal button. You may have never used it before, 1 over x. That takes the reciprocal of the value that I got for tangent, and so the value of cotangent negative 81 degrees is negative 0.1584. Now I'm going to ask you just to pause the video for a minute and try C and D, and then I'll uncover their answers, and you can make sure that you got the same thing I did. Then we'll go on to number 32. Here's what I got for part C and part D. Again, I didn't have a secant button, so I had to find cosine 202 degrees and then use my reciprocal button to flip it. It was very straightforward to enter sine of 97 degrees, so you should have all 4 of those answers. Now, number 32, we're given trigonometric, or we're given angles that don't have the degree symbol. If you don't have the degree symbol, that means your angle is being given to you in radians. So you want to make sure your calculator is in radian mode. If I just press my degree button again, I can see that the mode has changed to radians. And so to find sine of negative 0.11 on my calculator, I'll enter the 0.11, make it negative, and then take the sine. The sine of negative 0.11, rounded to 4 decimal places, is negative 1.098. All right. Enter those other 3 expressions. Just pause the video a minute and get those 3 answers, and then restart it and see if you got the same thing that I did. All right, let me give you one caution. I'm going to give it to you in one way, and then on page 338 you can look at it written in a different way. But there's something it's very important that you understand how significant parentheses are. Sorry, I forgot that you couldn't see that. How significant parentheses are when you are dealing, well, with anything in math, but that's certainly going to be true with trigonometric functions. If I write the sine of 20 squared, or let me just make this radians for no big reason. What about sine of 2 pi? No, that's not what I want either. Let's say I want the sine of 3 squared. Because there's no degree symbol, that 3 is in radians, not degrees. This indicates that the 3 is squared before you take the sine. That's the sine of 9. And you could punch sine of 9 on your calculator. Make sure you have your calculator in radian mode, because that's not degrees. That's not the same thing as this. This means it's the sine that's being squared, not the 3. That's equivalent to writing sine of 3 in parentheses, then squared. So if you want to square the sine instead of the argument of the sign, you either have to use parentheses or you put the square on the sign rather than the number. That's an important distinction. We're going to talk about that a lot when we get to calculus. All right, just a little bit more. Next, we have the 3 granddaddy Pythagorean identities of all times, the big 3. The big 3 Pythagorean identities that you're going to use so much, you're going to have them memorized very quickly. And I just want to show you where maybe the first one comes from, and then you can see where the other 2 comes from. The biggest Pythagorean identity of all is sine squared plus cosine squared equals 1. Or I should say sine squared theta plus cosine squared theta equals 1. It's easy to see why that is if you just draw a little triangle, label one of the acute angles theta, and then label the sides, the legs, length A and B, hypotenuse of length C, and then write down what you get for sine squared theta. Well, sine of theta is opposite over hypotenuse, so A over C. And then notice it's that being squared, not the theta. This is sine of theta, so we want to square the sine of theta. And for cosine squared, we would take the ratio of adjacent over hypotenuse, B over C, and square it. Now we're trying to prove this is true. I'm going to put a question mark to show that I haven't proven that yet. That's what I'm trying to do. If I remove the parentheses, I'll have a squared plus b squared over c squared equals 1. I actually did 2 things at once there because I was running out of room, but when you square both of these, you'll have a common denominator, so I went ahead and added the numerators. A squared plus b squared over c squared equals 1. Guess what you have if you multiply both sides by c squared? You just have the Pythagorean theorem, and you already know that that's true. So that's a very rough proof of why sine squared plus cosine squared equals 1. Now these other 2 trigonometric identities, or Pythagorean identities, can be obtained from this one. The first one, 1 plus tangent squared theta equals secant squared theta. If we just take the sine squared plus cosine squared equals 1, and I really haven't left enough room here to do a good job, but let me write that down again. Sine squared theta plus cosine squared theta equals 1. If I just divide both sides of this expression by sine squared, I didn't mean to have an equals there. I'm dividing both sides by sine squared. Notice what that will simplify to. Sine squared theta divided by sine squared theta is just 1. Cosine squared theta over sine squared theta, that is cotangent squared theta. And then the right-hand side, 1 over sine squared theta, is cosecant squared theta. And that's the third Pythagorean identity. If you just take the initial Pythagorean identity and divide both sides by sine squared, you get this one. If you divide both sides by cosine squared, you get this one. All right, the next set of problems say use the Pythagorean identities to write the expression as an integer. Now, here's the big three. And we're going to use them so much that they will be stuck in your head very soon. Let me tell you one thing before we get to number 36, and that's it doesn't matter what these arguments are as long as they're the same. They could both be theta, they could both be 2 gamma, they could both be duck. It doesn't matter as long as the arguments are the same. Sine square plus cosine square is 1. So 36 part A, I have cosecant squared 3 theta minus cotangent squared 3 theta. And it doesn't matter what these arguments are as long as they're the same. It's my third Pythagorean identity that involves cosecant and cotangent. How could I get this in this form? Cosecant minus cotangent. Or I should say cosecant squared minus cotangent squared. All I would have to do is subtract cotangent squared from both sides, and I'd have cosecant squared minus cotangent squared equals 1. So that's the value of this expression. Now the B part is not the same thing. It also involves cosecant squared minus cotangent squared, but you can't just say that's 1 because both of these have coefficients of 3. And those coefficients are the coefficients of the trig function, not the coefficients of the argument. You cannot factor a 3 out of these arguments, but you can factor a 3 out of these coefficients. By the way, that symbol is alpha. Now that I've factored a 3 out of both terms, I can say cosecant squared minus cotangent squared is 1. So that whole expression equals 3 times 1, or just 3. 38 is basically the same thing. In the A part, you can factor a 7 out of both of those coefficients. And that symbol is gamma. If you factor a 7 out of both terms, you have secant squared minus tangent squared. And if you look at this second Pythagorean identity, you can get it in the form secant squared minus tangent squared just by subtracting tangent squared from both sides. And you would have secant squared minus tangent squared equals 1. So the expression that we're given is 7 times 1, or 7. This last one, we have 7 secant squared gamma over 3 minus 7 tangent squared gamma over 3. Is it legal to factor out a 7? Yes, it is, because they are coefficients. Could we factor out a 1/3 and just leave the argument being gamma? No, you can't factor a constant out of these arguments. It doesn't matter that they're gamma over 3. What matters is that they're the same. So if I factored out a 7 from both coefficients, I would have secant squared gamma over 3 minus tangent squared gamma over 3, and the value of secant squared minus tangent squared is just 1. So that original expression is also 7 times 1, or just 7. All right, I want to do the first 4 problems on the next page of notes, and then we will stop and say that's all of day 1. And I know it's been over an hour. We're just accelerating just a little bit to get caught back up with the schedule. All right, 42 and 44 say simplify the expression. We have to get comfortable with doing all the same things with trigonometric expressions that we do with algebraic expressions. If I just gave you the expression, let's say a squared minus 4 over a squared minus a minus 6, and told you to simplify that expression, you would know, that you had to factor it, and then you could cancel your common factors. That's the difference of two squares. That's the easy kind of trinomial. That's exactly what we have here. That's the difference of two squares. And when you say, what's the square root of cotangent square alpha? It's just cotangent alpha. So, just like I factored the difference of two squares in algebra, I can do the same thing in trigonometry. Cotangent squared alpha minus 4 would be cotangent alpha plus 2 times cotangent alpha minus 2. And you can fold those back together to check it. That denominator, cotangent squared, pretty much has to be cotangent times cotangent. And then factors of 6 that have a sum of 1 are 3 and 2. And to get a negative 1 in the middle, you'd need a negative 3 and a positive 2. And then you can multiply that back together to check it. First would give you cotangent squared alpha. Outer would give you 2 cotangent alpha. Inner would give you negative 3 cotangent alpha. Those combine to give you negative 1 cotangent alpha, and negative 3 times 2 is negative 6. So I'm sure I have it factored correctly, and just like algebra, I can cancel my common factors, and I'll be left with cotangent alpha minus 2 over cotangent alpha minus 3. Now, would it be legal to cancel the cotangents and just say that's 2/3? It's not legal to cancel terms in algebra, so it's not legal to cancel terms in trigonometry. That's as far as that expression can be simplified. Number 44 is a complex rational expression. It's a baby fraction within a big fraction, and the way that's written with the sideways slash, it's a little bit hard for me to see exactly what's going on. I'm going to rewrite it with a more vertical representation of that fraction, and then I can really see it's a baby fraction within a big fraction. How do we simplify complex fractions? We multiply both the numerator and the denominator by the LCD of the baby fractions. The LCD of the baby fractions is sine square theta. Now, I kind of wish that I had put a middle step. Oh, I know how to fix it. Just in case anybody needs this middle step, I'm going to write both of those cosecants as 1 over sine theta. And I'm multiplying by the LCD, I just have it to the left of my complex fraction instead of to the right. I can still see that when I multiply sine squared by all 4 terms, the first term in the numerator would just leave me sine theta. The second term in the numerator would leave me sine square theta. First term in the denominator would just leave me 1. And the second term in the denominator would just leave me sine theta. Sine squared times 1 over sine One of the signs cancels, just leaves me the other sign. Now I've cleaned up my complex fraction. I may be able to do more if either the numerator or denominator will factor. And I can see that I can factor a sine theta out of the numerator. And then I do have a common factor. That whole expression that we started with simplifies to just sine theta. So in calculus, whatever that is, we have problems that say find the derivative, whatever that is. Well, you can imagine that whatever find the derivative means, it would be a whole lot easier to find the derivative of this than it is to find the derivative of this. That's why we need to be able to simplify trigonometric expressions. All right, these will be our last two problems for day one. Both of them say use the fundamental identities to write the first expression in terms of the second. So we want to start with tangent, but somehow we want to rewrite tangent in terms of something that only has cosine in it. We have to start with tangent and end up with an expression that only has cosines in it. Well, I can start with the definition of tangent. Really the alternate definition that I mentioned. Tangent theta is sine theta over cosine theta. But that's not exactly what we're going for because we want an expression that only has cosines in it. Somehow we have to change this sign to a cosine. Here's our hint. Use the fundamental identities, the fundamental Pythagorean identities, the first of which is sine squared theta plus cosine squared theta equals 1. That gives us a tool for changing this sign to something that only has cosines and numbers in it. If we solve this first Pythagorean identity for sine, we would have to subtract cosine squared from both sides and then take the square root of both sides. We're not worried about plus and minuses right now because we're only dealing with acute angles. But we can say that sine theta is just the square root of 1 minus cosine square theta, and the denominator is cosine theta. Again, that was just from looking at sine and thinking of how to get it in terms of cosine, or solving this first Pythagorean identity for sine. Subtract the cosine square from both sides, take the square root of both sides, then we have tangent in terms of only cosine. This last one says start with cosecant and end up with something that only has cosines in it. Well, the definition of cosecant has a sine in it, not a cosine. But we know how to change a sine to a cosine. That's what we did right here. So cosecant theta is 1 over whatever I can put in place of sine theta that only has cosines in it. We said sine theta equals the square root of 1 minus cosine square theta. So we can take one trigonometric expression and write it in terms of other trigonometric expressions. All right, that's all we need to do for day one, and I apologize, I do know that it was more than an hour, but the homework for day one is on the 3rd page of notes. I'm looking for my 3rd page of notes. Ah, there it is. The homework for day one of 5.2 is page 346, odds 3 through 25 and 29 through 49. Have a good day.